Recording, and can I get a shout out from anyone in Discord just to let me know that we're hearing you?
Yes.
Okay, great. All right. So a quorum or a majority of people should be able to see grades for the last project. There's still a few. I'm still kind of working out a few. The process wound up being a little bit longer than I expected because I was having lots of fun reviewing code and stuff with my new feature point system. So in case you're wondering kind of where we're at, I mean, I think so. It's usually, like I said, it's always 10 points per project for sort of my take on how well you kind of complied with the prompt and overall how things went. And then there's the feature points. So overall, I think the typical spread right now, certainly if you've got 40 or more overall points, you're in fantastic shape. Few people a little bit below there, a couple of people above there. So it's a matter of sort of how ambitious you've been about kind of adopting and putting in other features. Sometimes jumping ahead, you can tell who's used Unity before. And some people, I think you're just kind of waiting to spring all sorts of cool sound effects and stuff on me in some of the final later on projects. I'm always one. I like to see sound in games, so that's always a piece of it. If I from here on out, especially games just don't feel finished unless they have sound to them as well. So always include that in there. Just to make things more reactive and fun and full and so on. Let's see, other things about the project. There was really, I think everybody's doing pretty well. There's, I think, 2 remaining kind of odd issues with Unity teams, but we seem to have that well in hand, so we're pretty good. What were other feedback things? Yeah, I think we're in pretty good shape. So last time we talked about largely the NPC, the beginnings of AI and how we can kind of build convincing enemies. And even we had our, of course, our enemy or our antagonist, I should say, our antagonist in the apple tree game, where the antagonist went across the top of the screen and did all sorts of wonderful stuff. But now we're talking more about things that are far more independent and free roaming and so on. So these sort of things like our tanks here, and I've spent a little more time getting my tanks chasing around my player in a hopefully more sort of convincing way at this point. And I mentioned last time, one of the things that was really kind of bothering me was that they seemed, as they were aiming their turrets, they would shoot, and the bullet wouldn't seem to come right out of the turret. And it was the first time I had just used a constant force component on things, and for some reason that doesn't quite keep up as well or as nicely as just giving an object a beginning velocity when you instantiate it. So that was one weird thing. If you're ever working on bullets, it's better to projectiles. It's better to add things in script. A little bit of weird things going on with the constant force component at this point. So in the meantime, these are using a combination mostly of casting to decide can we see this little player in here, and I'm going to navigate the player. I'm going to kind of hide our little apple behind these barricades over here. You'll notice that the tanks stop shooting because they can't see behind the barricades there. Occasionally they can see through, and they'll decide to take a shot. But they're going about their business, and they almost seem fairly, well, I don't know, they seem fairly convincing in terms of their patrolling action. They like to patrol around sort of the center of the screen, stay relatively near there, and when they see one another or see an obstacle ahead, they'll try to avoid it just by doing some simple turning. In extreme cases, I've added a new behavior, and it's going to be one of the foundations for one of the things we're going to talk about today. So I'll bring my little player around here. You'll notice they'll start shooting it. But I'm just going to click on the player, and you'll notice that immediately, if anyone is nearby, I'm going to try to get a whole bunch of them nearby, they'll back off. They'll move away from the player as sort of a special case. All right, so it's I liken it to the Pac-Man power pellet kind of thing, where somehow, maybe it's a depth charge, maybe it's a, I don't know, whatever we want it to be, some kind of force field activated thing. Anyone begins to push away from it, they react to something going on. Maybe it's just, if those of you are any Dungeons and Dragons fans out there, it's our bard object suddenly used a vicious mockery cantrip or something. Everyone had to run away from him because they just said something awful that they couldn't bear. But that's going to be one of the, not vicious mockery, but that sort of reaction or group reaction or event-based reaction is going to be one of the key things we're going to talk about today. Let's see, I have my mask upside down? I always feel like I think I do. No. Just me talking about this. So, in order to make that happen, there's a couple of things I want to talk about. Make sure I get the right slide deck here. So, I have two slide decks, and they're sort of related, and we'll kind of see where we get with one and get the other, and give you a bunch of great ideas. Some of you, I noticed, have done, snuck ahead, started using coroutines and interpolation and some other things in there, which is cool, but wanted to get these concepts, sneak them in there before the break so you can be thinking about your design of your game as well. So these are kind of good food for thought topics. All right, so events or delegates, or events and delegates, the publisher-subscriber pattern. This is one of the key kind of alert group, hive mind, sensing techniques that can get used. And the notion is that there's some sort of event that occurs that some other group of objects have said, yes, we're interested in that sort of thing. Tell us when that occurs. Now, if you think about it, that's largely what's going on in most of Unity, and things like, tell me when I'm awakened. Tell me when a frame has been updated. Tell me when another object has collided with me, right? Those types of events. So that's even deeper. It's not just an AI technique or NPC technique. It's something that's fundamental to the whole structure of Unity and the engine itself, right? So these sort of events are another means of talking between classes, right? So we have components that are our classes, and some of you have done things in your projects, and we've seen like, okay, well, if I want to talk to a component on another object, I typically will have to know. Sorry, I got a lawnmower outside. Hopefully not going to be there all day or all class. I typically have to know about that object, and then I say, well, let me get the component, let me get the class that I'm interested in talking to, and then I can call a method, a public method on that component, or I could access a public variable on that component, like when I access the velocity of a rigid body, right? That's some means for me to go and look at another component, look at another class, and modify it somehow. So that would be me talking to another class just by referencing some public variable or public method. So these have been explicit direct object references talking across objects, like I say, player, get, game object find player, then get component, rigid body, very explicit. I have to go through and say exactly what I want to do, and then ultimately exactly the field I want, and so on, right? I need to know at that point is when I do it, right? Sometimes we use static, like when we define something, when we say, okay, this class, this component has one specific thing about it that is shared across that whole class that all of the members of that class might need to know about. Or in the case of a library, like our math library or our physics 2D libraries and so on, we might say mathf dot absolute or clamp or one of those to get at things, because we know there's only one version of that function, so we kind of declare things appropriately, and then we can kind of reference them by class and not by object, right? So we don't have to have a specific instance of a game object or an instance of a rigid body that we figure out what it is. We just say, okay, physics 2D dot circle cast, right? Because it's just a one circle cast method that's shared by all of physics 2D, for example. Right. But is there a better way to communicate? Well, better is a silly way of putting it. Is there another way of doing it that isn't quite so specific or quite so direct, that we can kind of abstract ourselves or extract the process a little bit? And for that, we'll just think of it as, I could just think of it as being yet another way, and that's where events sort of come in, right? Like in the case of the start event or the update event, we really don't think about, who's calling me, or, specifically what am I even calling? I'm just saying, okay, update everything. I don't have to know, what objects are there, or what, I just need to sort of know, like, ultimately it's, if we thought about it, it'd be like monobehavior dot update, right? Because everything came from monobehaviors, so therefore everything, we're just calling the method that all of the monobehaviors have. So that's sort of like where events come in. Events are used by one class to notify other classes when a specific action has occurred, so that those other classes can execute some desired behavior. They all don't have to have the same behavior, right? There may be NPCs that run away, and there may be NPCs that come to aid the player, right? There may be things that fall apart and things that come together. Doesn't matter what they are, they're just all reacting to an event, and it's up to each one of those to implement what it is that they want to implement. Like, just as in our case, there's no rules necessarily about what you put inside update. You just know when it's going to happen. You just know that's when an update is going to occur. Or what goes on inside your collision, that's up to you. You just know it occurs as a reaction to when something happens. So far we have been tapping into events handled directly by Unity. For example, collisions, button presses, frame updates, and so on. But we can also use our own events to be triggered. And we think of it as it's a two-part conversation, right? This is where the publisher-subscriber pattern gets its name. Events have a publisher who raises the event and subscribers who listen for that event to occur. A publisher can listen for their own event to occur if we wanted, right? So a publisher can be a subscriber and vice versa, same thing, but they don't need to be, right? Generally, though, an event will only have a single publisher and some or any number of subscribers. Can you break that rule? Yes. Do I recommend you break that rule? Not right away, not first time out. Generally, there's supposed to be, one person gets to call the event and everybody else gets to react to it. There's no reason you couldn't go beyond there, but then it wouldn't just be publisher-subscriber anymore. So one important thing about events or publishing and subscribing, an events publisher has no direct reference to any of its subscribers. It does not know or care about what other classes are listening to that event. It just raises its event, and everybody does whatever they respond to, right? It doesn't have to know. The fact that the player got hurt, it doesn't know that somebody else is going to come to its aid. It just knows it's saying, I got hurt. We'll see what happens after that. Right. Now, in order to make this happen, in Unity especially, and there's lots of different ways to do it, in other languages. You can implement it however you like in whatever game engine you like. But in Unity, we're going to be using a special, some secret sauce for events called delegates. It's one of the features of the C# language. Delegates are sort of the C# equivalent of function pointers. Pointers in C# definitely a little bit fuzzier, friendlier, more, less intense than pointers in C and C++. So we're going to use, where we might use a function pointer in C++ or C, we probably would use a delegate in C#. Right? You use them when you want to have a function whose value may change, right? When you're not sure, or maybe you have, right now this function does this. Maybe later on, calling that function or calling that delegate may have been reassigned to do something else, right? You can substitute functionality in where that delegate gets called, potentially. So you can use them when you want to dynamically change functionality without necessarily using conditionals. What I mean by that is you don't have to say, if this happened, do this. If this happened, do that. If this setup is this, and so on. You could say, well, okay, I want this to happen in response to this, and I want something else in response to something else. Or you could say, well, let me go in and change what's going to happen in response to that. And just change the delegate, and then next time that event occurs, the new delegate would get called instead of the old one. So one of the things you have to be careful of when you are using delegates is not to invoke them if they are null. If you have a null delegate and you say, okay, go ahead and invoke that null thing, bad things could happen. We don't like dereferencing nulls, we don't like invoking nulls, and so on. So we want to be careful. Now, here's the basic implementation. Here's a basic implementation for the publisher side. So say we have our class, which is going to be a publisher, and it doesn't have to be, the publisher class could be doing lots and lots of other things. This just happens to be here. It could be our player. So the player might have this within there, but just for sake of argument, there it is. So the publisher has some event that we want to trigger. And first thing we need to do is to sort of decide, well, what is the type of that event as well, right? So we have to declare it so we know if and when it happens, what parameters might it get passed, what return value might it have. We don't really use return values, but mostly about what parameters would be passed to it. So what can it expect, right? If you say, oh, okay, on collision, we know that's a collider 2D, or on collision 2D, it gets back a collider 2D, and so on, right? Those are the things that get passed to it, so that's what happened. So we have the same sort of thing. We'd set up the type of the delegate. So the first thing here, public delegate void, meaning it's going to return a void, event to be triggered. It doesn't expect any parameters, but so this is going to be the typical event to be triggered. And then we create a static event with the delegate that can be accessed by the other classes. This becomes the real thing that will get called. Right? So it's of the type event to be triggered, matching this up here, and this is its name, on event to be triggered. So somewhere here in our routine, in our Pac-Man eats the power pellet method, it says, okay, let's go ahead and trigger that event, right? So this would be, I ate the power pellet. Invoke. If anyone's listening to me, listening out for me eating the power pellet, they would now be informed had they already subscribed. I use this null dereference watch, this question mark dot, to make sure, just in case nobody's listening, I don't invoke a null list. Right? I don't invoke a null delegate. On the subscriber side, this is how we basically subscribe. We do have to know, in this case, who we're subscribing to. So it's not a completely anonymous conversation at this point. The setup is not necessarily entirely anonymous. You have to know, what are you listening for? So you have to know, I want to listen for Pac-Man about to eat the power pellet. So imagine we have publisher dot on event to be triggered. This is why it's nice that it's declared static. It's out there for everybody to see. And we just say plus equals do something in response. This is my local version. This would be my, what do I want to do? Do I want to freak out? Do I want to run to their aid? Do I want to, what? It could be anything as long as it has that same signature. You know, it's a void. It doesn't take any arguments. We can plug that in. So this is its setting it up. This is getting rid of it, right? It's convenient to do it on enable, on disable, so that when it comes into existence, when it goes out of existence for whatever reason, it adds itself, and then on disable, it removes itself from there, right? So if an object is destroyed, if an enemy goes out of existence, if a compadre winds up leaving the map, it can take themselves, you know, they'll leave the, they'll no longer be subscribed. But this is where they do their stuff, in that do something in response chunk. So, as an exercise, not going to be collected, not going to be graded, but you can create a class that triggers an event when the player presses the space bar, or what I did in mine is I just waited for an on mouse down event on my little Apple object. And I had, in my case, just one class that subscribed to that event, and I had them all enter a fleeing state when it would see that that event had occurred. So you can go ahead and, you know, try that and use the basic syntax of that. So if we were to look at my version over here, so we have the player here, and the shmup controller. So you can see there's a delegate void on alert, and we set it up to be my alert in here. So in here, here's my alert, and I know if anyone is now listening to my alert, on mouse down on my object is the one. Right? On mouse down means the mouse is clicked on top of this particular object. Right? So it's a convenient way to do picking of an object on the screen. Don't have to get too fancy, just on mouse down. Handy thing to have, right? So at this point, my alert gets invoked, and the class that I have listening for it is the NPC movement class or component, because that seemed like the obvious thing to do. And I added a new state called alerted, and I just did it here because there's no destruction, or, you know, nobody ever leaves the game just yet. I just had it in the start for here that we would go ahead and add on alert to the alert, right? So the on alert here is this method here, right? That's the on alert. It'd be like on collision enter 2D, update, whatever it is. So I'm going to say add this method to the shmup controller's my alert. Right, so we've added it up there. And what the NPC does when it receives that event, it says, all right, well, am I close enough to the player? It assumes at this point that that came from the player. We could have done something like said, well, okay, maybe this event should tell it that it came from the player. Could have done that as an argument. But in this case, it knows that, or it assumes that the alert came from the player. So it says, okay, how far am I from the player? If I am closer than 5 meters, then I should change my state to alerted. If I'm further than 5 meters, I don't care. I didn't hear it. Maybe that's the limitations of my sonar, the limitations of my hearing. Fill in the blank what you think it's a limitation of. So you can decide, do I want to react to it or not? So I would go into my alerted state, and my NPC machine, which is just happening over and over and over and over again as part of my update, it would, of course, go through, and the next time it gets called, it looks at my state and says, okay, I've got a little state here for alerted, which executes this. And ultimately, I decided to get a little bit fancy as well. I said, well, first off, if I'm alerted, and what did I do? I said, well, if I started playing with if I'm facing the player or not, because I wanted to do this kind of thing where I would either turn and run away or just immediately start going in the opposite direction. And I figured out, well, I could, if I'm not facing or if I am facing the player, I immediately just go into this retreating state as opposed to kind of turning and avoiding. Right? So it's a little bit sophisticated in terms of once I'm alerted, I can go into this retreat mode, or I just sort of rotate around or rotate away from it and avoid it, as opposed to if I'm really facing it, I just go into this retreating state. I could have handled these two cases, I suppose, as just different state or as one state and special versions in there, but I figured it'd be cleaner to have this notion of suddenly if I need to go backwards and wander away, trying to retreat from something, I made that a special case so I could do that. But for now, the important part is that we're saying we're switching our state machine into this alerted state, and then it'll take whatever action is necessary. Now, I could do things like decide, all right, after I receive that alert, I could stop subscribing to that event if I wanted. I don't have to only unsubscribe if I go away. I can say, well, I subscribed, I listened for it, and now I'm done. I can only hear it once. Or I can just go ahead and leave myself subscribed, and then every time the event happens, it'll keep happening over again. I'll always know about it. Lots of options. Lots of options in that case. So, very useful. So, events, sometimes you can offer an alternative to things like the singleton pattern. Singleton being, of course, we only want one thing of one type. We only want this one thing to happen. Now we've got a way here to say, well, okay, there's one thing that can be the source of something that lets everybody else know, right? Instead of everyone having to look to see, oh, is there an open chair that I can try to sit on during our game of musical chairs? It could very well be one person hops into the chair and yells, and everybody else runs away because, we know that only one thing or something has triggered that alert, and everybody else is listening to it, right? So it's another option for having this decoupling, right? One part of your code can trigger an event without knowing or caring what is listening. You can add new behaviors to an event without going back and changing your original code, right? If I have a new enemy that reacts in some different way, it doesn't matter to the player what happened. It just is all part of the enemy, right? So it's nice in that it's kind of got this code decoupling where you can implement new stuff without having to change your original code. One really nice thing about it. One of the caveats, though, or the things to worry about, is that sometimes it can make your code more difficult to follow because you don't really kind of know, okay, who is calling me or what happens as a result of this, right? You can't just say, well, I know exactly who's going to respond to it because maybe some other code plugged itself into it, right? Someone is eavesdropping on your conversation. How do you know? You don't know. So code can be a little bit more complicated to follow, but it is nice in that you can kind of have this clean interface to say, all right, I want you to do something for me. I'll handle the implementation. You just tell me when I should be called. Right? It's a nice arm's length relationship, a decoupled relationship there. So imagine when our player collides with an enemy, we could simply trigger an event, which would then picked up by things like our audio manager, our game manager, our UI manager, and so on. Right? We could have a collision. Now we could do something like say, well, on score needs to be updated. Do this. Or on collided with the player, or just use that as a convenient way to have everybody listen, and the player would just say, I died, and then the audio manager would play the right sound, the score would do the right thing, the UI would show on the screen, and so on, all as a result of the player just saying, I died, right? Without the player having to call that code. It just sets up that magic event. So that's the basics. That's the kind of underlying stuff. Now, Unity goes a little bit further because Unity can. After all, Unity uses C#, but Unity does more. And so there's a specialization called Unity events, or the events that we're using that you may have seen, you have definitely seen, I should say, on click, like when we clicked our buttons and so on. It is using things under the covers, but it's more specialized that you saw when working with a canvas. And you may want to potentially in your scripts, how do I say, well, I want to listen for a button to be clicked without going through the GUI and so on, right? So if you can add yourself to a script on the fly, add yourself to a published event, how do we do that, right? Well, it turns out you can actually declare your own Unity events, and you can listen for Unity events if you want to go in that route, right? So there's specifically Unity engine.events. So within your script, if you want to use Unity events, add that to your script. You can declare an event a lot like when we declared the event using a delegate, but now we specifically used a Unity event for it. And then we invoke it just like we would have invoked our delegate or our published event. The listeners, on the other hand, we can explicitly add code, just like when we dragged and dropped our on button, north, south, and so on. We can actually add our methods into these Unity events. So you could add listeners to Unity events that exist, right? Or anything that's been made. Right? Why do we do these things? Like I said, one of the most important reasons to use events, listeners, observers, etc., is to decouple classes from one another, to create an explicit, clean interface between them, so that we don't have to implement the behavior of the bomb when it blows up in response to the player bumping into it. Right? We just say the player bumps into something, and then the bomb says, "Oh, I got bumped into. I could do my own thing." Right? We can keep the code separated. That's what I mean by decoupling. We'll learn a lot more about decoupling and other object-oriented techniques as we get into inheritance. Some people really flexed and already implemented inheritance in their project. That was fun to see. But the basic subscribe, publish pattern, would love to see that in code. It's really nice, especially in the kind of the shoot 'em up game, where when you trigger something, you want to have the environment do something kind of more complex behaviors, and especially with regards to sensing, right? Something happens, an explosion goes off, and you want everyone to know about it. Classic example. Someone reaches the alarm, that bad guy runs away, manages to get close enough to hit the switch. Which is the one I'm always playing? It's the worst thing when an alarm goes off and suddenly you have to hide and wait for the alarm to die down. And BioShock, I think, is always running and hiding in places. Anyway, that sort of thing. All right, so we'll leave that for now. Now, coroutines. I want to talk about coroutines. They're really useful again, it's not just an AI feature, but as we talk about things happening in response or things happening that are more involved, kind of complex behaviors and so on, it makes sense to talk about coroutines, because they're a very, very efficient way to implement code or to implement things that need to basically be executed incrementally. Right? There's like, do this, then do this, then do this, or keep doing it in a loop, but loop this number many times and then go. But within that, you may need to allow other things to happen. Right? That's one of the challenges of game programming, working inside a game engine, is that you shouldn't just take over and hang inside a loop for a long time, right? You've got something to do and you want to carefully trace out this wonderful path and then do that and then change the color and so on. You can't stop everybody else while that's going on. You need to let code execute. So really complex update routines where there's tons and tons of stuff going on, that can cause your game to have those wonderful lurchy sort of things where your player is supposed to be running across and it just freezes for a moment because it's thinking about something and it tries to move again, kind of lurches because somebody's just consuming too much time, not yielding back to the main thread so that things can run. That's why we think about incrementally executing things. So we have a spot the problem here. Now, I'm going to talk about interpolating a bit more in just a second, but I'm going to give you the quick version in here. So imagine we want to interpolate an X position, right? We want the player or an object or something to move from one X position to another X position over the course of some time, right? So we have a starting value and an ending value, and we want to move in between those, or interpolate between those two numbers, right? Interpolation. Assume we have t, which is the current time that we're at, the current time step, and we have the starting value and ending value that are declared. We started off at 0, we want to get to 10, and we want it to take a certain amount of time to move in between, right? So we say, well, we want to move over the course of, say, 2 seconds. We want to move from A to B. So we grab the current time. We say, this is the time we started this movement. And we can say, well, we have the certain amount of time that it's going to take. We know it's going to take 2 seconds to get there. So we could say, well, the current time, time.time is always our current time, right? Time.time minus the time at which we started. So that gives us the elapsed time, right? The current time minus some starting time. That's our elapsed time. That's going to initially when it goes in here, it's going to be 0. We started at 0, and then as time passes, that's going to increase until we get to 2, right? That's our lerp time, our interpolation time, how much time we want to take to do this action. All right, you can see what the action is. We say, well, let's figure out the fraction, the amount of time, the percentage of the time that has passed. So say the elapsed time over the total time, that gives us the fraction of time that has passed. When 2 seconds have passed, this t would be 1, right? So it's going to go from 0 to 1 incrementally. Hint there. So we just say, all right, let's move from the starting value to the ending value, and t, in the case of interpolation, means it starts off, if it's 0, give us this value. If it was 1, give us this value. Anything in between, if it was 0.5, crash course in interpolation, if it's 0.5, it's halfway between these two. It's a mix of those two things. Right? So as this number goes from 0 to 1, it should smoothly move between or mix between these two numbers. Right? And we don't care about X, Y, and Z. We're just going to keep those. Right? So that seems like a good way to move from 0 to whatever number, our start value to our ending value. Right? Anyone spot the problem, though? Yeah?
If this is running an update, then wouldn't start time and that time always be the same?
Start time and...
Because you said if
Well,
Be zero.
it's set it up here. It would be 0 for starters, right? So we'd come into the loop. It would be 0 here. Time.time, let's assume that somehow time.time is passing. So let's assume that we're not in a dead loop, which would be basically the problem. Right? So even if this weren't dead, it still wouldn't work. So your point is absolutely correct in that if this never increases, they're the same, it's always 0 and you're just dead in the loop, right? Is that
Yeah.
okay?
It's just running, so it's going to be an update.
Right, it would just infinitely loop there if time.time didn't pass. Now if we were really lucky and somehow there was a time.time was being updated in another thread even, then time would pass, but we would still not get out of update for the 2 seconds that it takes to run this. Right? So maybe we are lucky and have a timing thread that's happening, so time is passing, but we know that we're stuck inside of this one update loop. Because nowhere in here are we doing any sort of yielding. We're never giving back any time to the system to do anything. It's just a bad loop, right? A bad tight loop. And we certainly don't want to spend, even if it ran correctly, we wouldn't want to dedicate 2 seconds to this, right? Other things should have a chance to do stuff. So along come coroutines, right? We want to give other stuff a chance to happen within there. Now, if you wanted to get really fancy and have it drop out and each time check with the time and so on and kind of implement your own way of saying, okay, I'm not done yet, just run according to time.delta time and maybe keep track and so on, you could get fancy. You could say, well, okay, don't make this a while loop, make it an if statement, and then say, okay, elapsed time is the start time minus, or, you know, use the delta time and keep track. You could do that. But coroutines are kind of a cleaner way to do that. So coroutines are special functions that are designed to be executed in intervals or incrementally. That's why they're typed IEnumerator. It's a C# thing, right? You're incrementally executing. They're allowed to exit prematurely. We had break and return and things like that. You can do that in order to break loops or return from a method if you wanted. But the cool thing about coroutines is when you have a typical yielding, a yield in there, they resume where you've left them when called again. So that happens kind of automatically. So you can say, okay, stop what I'm doing until something happens, and it'll go back to the system and happily do the right thing. So it's super useful for, say, kicking off a process that needs to run over the course of several frames or several seconds or whatever, and letting them just kind of run out on their own, and you don't have to worry about them stopping. You still have to design them right. You have to put the right yields in. So you can also do things like create routines that have to wait for another operation to complete. So let's do the, well, I guess let's look at how you would use yield, right? So if you say yield return null, that just means, okay, stop for now and come back to the next line of code after the next update, right? So it would basically mean in this code, if we had a yield in here, we wouldn't want to do this inside of already inside of one update, because that would kind of break update. So don't put yields inside your update call. But take this whole thing out. If you took this whole thing out and made it a coroutine, and you had a yield in here, it would say, all right, effectively, it would become yet another update loop for just that little bit, right? Because it's going to run once, wait for the next update, run again, wait for the next update, run again. So you can create your own little private, distinct, doesn't bother anybody else update routine if you want to do that. And the nice thing is it doesn't just come back to the beginning again, it comes back to exactly where you left off, where you yielded. You can also say yield break, which stops the coroutine immediately there, you can say yield return new, wait for seconds. So you can say, well, okay, I'm done for now. Come back to me after a certain amount of time has passed. Right? So if you know that 2 seconds from now you want something to happen, or say you are animating something and you know you have 12 frames per second of animation or something like that, and you know that your update rate, well, you don't know what your update rate is. So you want to make it so that it only changes the image every 1/12 of a second. You could say, well, wait for a 1/12 of a second and change the texture, change the bitmap, change the sprite. Now, you can also execute this or stop after all of the rendering and the GUI is complete. So it's not after the next update, it's at the end of all updating. Right? So you can customize where in the Unity loop this happens. You could also say yield return new, wait for fixed update. So this will mean this will now run at the end of the next physics step after all physics have been calculated. For now, we'll focus on, basically there are going to be 3 of these that are going to be most important for us for starters. This is a yield return start, another coroutine. This is kind of cool. You can say, okay, I'm done for here until something else happens, and you can kick off yet another coroutine and wait for that coroutine to complete. Right. So useful for setting up sort of an execution hierarchy. But for now, and in the typical usage in the projects here are, first one's to try this simple yield return null and yield return new wait for seconds. Those are going to be your 99%ers, right, in terms of yields. So if we look back at our problem loop and we try to do it as a coroutine, this would mean, okay, when it's time to do this, don't do this in update, right? You probably don't want to call this from, you could do it, call an update if you only call it once. Don't repeatedly call this, because this is going to take care of that whole 2-second move. So you're just going to kick this off somewhere, and you're going to say, start coroutine for this. And the important part is it's using this yield return null, which means at this is going to execute after each frame update. So on my computer, running on my built-in screen, this will run basically at 144 hertz. Right, so it's not going to get in the way of anything else. And we would invoke it as like this, start coroutine move. Just kick that off. Very, 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 very useful for, you want to go tell an NPC to go do something, and it's a complex thing it's going to do. It's also great for animating, basically animating simple values, like say you want to fade something in or fade it out, or move something, or, create simple animations or animated parameters. Lots of good uses for that. So I mentioned interpolation. Wanted to make sure this other part. Yeah. All right. So let's go through interpolation and animation. Sort of another chunk of creating things that are convincing, things that change naturally, that over the course of time move in very sort of natural ways without getting into all of the physics behind it, right? Getting into accelerations and decelerations and so on. Most people, when they learn animation, like hand-drawn animations or stop-motion animation, they don't study physics. They study what is happening, what natural behaviors and so on. So we'll approach it from that perspective, not the physics perspective. So we have to talk about the sort of things that we might interpolate, and then how do we interpolate them? So first question, will it blend? Anyone remember that? It used to be one of the early internet meme videos. Will it blend? This guy would blend all kinds of things, iPhones and anything in the Blend Tech 2000. So, will it blend? Averaging and blending. We're going to power through these. None of these, the math in here is not designed to be difficult. So, average between 2 and 6, you should immediately be able to say, average of 2 and 6. Okay, someone shouted 4. Good. How did you know? Well, maybe you did this, right? Maybe you did 2 plus 6 divided by 2. That's typical of the average, right? You add up all your values and you divide by the number of samples you have there. So A plus B over 2. Sum over the count, right? Now, here's an unlabeled number line. I said, well, okay, what's the average between those two things? Say, well, okay, that probably is, well, we don't have an equation. How can we figure that out? You probably said, well, it's going to be this point in between. For those who are listening online, the point in between these two is the one, right? That's the average of the two. You don't really need to know what either of those two numbers really are at all. You just know what? You need to know that it's halfway between the other two, right? There it is. Now we can start getting fancier with these tough questions here. What's the number that's 25% of the way between those two numbers? Well, first you'd say to yourself, well, 25% of the way in which direction, right? Can't just say 25%. Let's assume 25% from the first number, right? So for 25% of the way from the first number, it would be the first number plus 1/4 of the distance between the two, right? That would get us there, 1 unit along the line there, because we were 4 units apart, so 25% of the way is 1 unit along the way. So if we think about this in terms of our original A plus B over 2, we could think, okay, well, we have basically, this isn't, not calculus. Same thing as A over 2 plus B over 2, or half of A plus half of B. The average of two numbers is, in this case, well, in all cases, it'd be half of one number plus half of the other number, right? Which is just, I thought, the more you think about it, it's funny, the obvious things, sometimes you think harder and harder about them, the more it blows your mind, right? It's half of one plus half of the other. 50-50 blend of A and B. So we start thinking of these things in terms of their coefficients, right? Start thinking of these averages in a little bit of a different way. It's not just a sum divided by the whole, it's actually a coefficient, an amount of each number. In this case, if we have 2 of them, it's easy. It's just some blend, some mix of the two. Say a 50-50 mix of A and B right in between. We can mix things unevenly, like our case of our 75-25, right? 1/4 of the way past A turns out to be 75% of A plus 25% of B, or a 75-25 blend of A and B. These are the weights of the blend. Use any blending weights you want, as long as they add up to 100. If you go beyond 100, well, that's kind of weird. You're basically saying none of A and extra amounts of B. A little bit weird. So if we think about it again, straight math, 25% of the way between 2 and 6, we know distance between them is 4. So we can say, let's take 2 plus 1/4 of the distance, we get 3. Right? 75% of 2 plus 25% of 6, which gives us our coefficients here. So generally, we're saying we have, say we start off with our coefficients, we'll call them S and T. Here's a hint, we saw T before when I started talking about coroutines, we wanted to have t be the value that went from 0 to 1 as we moved from one x position to the other x position. So if s is how much of A we want and t is how much of B we want, we know that they have to add up to 1, so we know s is 1 minus t. So we can eliminate s and just say, well, think of it just in terms of t, because we have t being subtracted from 1. So we control the balance of the entire blend by changing just one number t. That was our lerp value that we had. We said starting value, ending value, and then how far between them do we want to go? Right, we want to start at 0, end up at 1. We want to move backwards, we can be at 1, move our way back towards 0. So if we wanted to move forward and back, we could go from 0 to 1. We could use the sine function or something like that for t. A little bit weird. Wouldn't exactly be linear at that point, but, well, let's think about that in a minute. So these are two compatible views here, 1 minus t times a plus t times b, which is blend sum of a with sum of b. Right? Or we can think of it as sum of a is basically subtracted from a, and some amount of b is added to it. Start with a and add some of the distance between the two. So when t is 0, we get a. When t is 1, we get b. However you want to think about it, it's basically you have a knob. You have your time knob, your t, and you tune it to get the blend between the two. It's just a float that ranges between 0 and 1. So we have numbers. We talked about blending numbers. Easy enough to do. We know how to average two numbers, or But can we do other things? Can we blend compound data? We certainly can. Blend more than just floats. You can blend 2D and 3D vectors, for example. Right? You just decompose each vector into its components and simultaneously blend each of those dimensions. Oh, I ran out of space in there. That should be x, y, and z. Right? So say we had a vector 2, we want to move along the vector, 35% of the distance is 35% of by minus ay, 35% of bx minus ax, and continuing on. Pretty cool. Can we blend anything? Well, mathematically we can. Does that actually give us results we want to use? Not always. Not quite. We can't always blend anything we want. Certainly if we have the vectors, we can do it. But not all compound data types will blend correctly with this approach. For example, if you have RGBs or Euler angles, certain matrices, certain quaternions specifically, there are a bunch of things that you wouldn't want to use normal linear interpolation on. Have we talked about quaternions much? We kind of mentioned them in terms of, there's sort of a magical rotation that we use to avoid gimbal lock, and we express this, an orientation by having an angle and a rotation around that angle. Right? We can't just linearly interpolate those sorts of things. Turns out we use something called slurping, spherical linear interpolation, to kind of help with that, where we actually think of it as, being spherical, and we won't really talk too much about that. But there are reasons for those. And also, let's think about a simpler case. In the case of RGB, say you had bright red and bright green. You said, well, what's halfway in between? Gives you sort of a dull, swampy color in between, where you might have thought you wanted to get, this bright yellow, because the differences between subtractive color and additive color, and this ways that color works, that works in one model and not the other. Or it'll give you something predictable, but maybe not what your intuition would tell you. So because of that, many compound classes like RGB, you may need to write your own blend, or you may need to convert from one thing to another. Like even in the case of quaternions, you may wind up saying, okay, let me convert from here to a matrix, or if you have a matrix, you might need to pull out the rotation values from that matrix, do a quaternion mix on those, and then do a linear interpolation on the translations, et cetera, right? So you might need to write your own blend method that does the right thing, whatever that may be. So in the case of color, you might do something where if you wanted to interpolate red, green, and blues, you might convert to hue, saturation, and value, a different color space. Right? Lots of different ways to express color. Hue, saturation, and value, brightness and chromaticity, all sorts of different things. And then do your conversions, do your mixes there, convert back to RGB when you're done. Right? You always convert between different spaces. We'll come back to what happens when you try to blend Euler angles, maybe a little bit with issues with gimbal lock and that sort of thing. But we'll just need to be aware of them. So technically what we're doing is constructing new data points within the range of a discrete set of known data points. This, of course, is interpolation. Dun, dun, dun. Importantly for us, though, when normally we're talking about interpolation, we often are talking about changing those blend weights over time, right? When we're animating things, we're moving from a starting position to an ending position over the course of time. And we may, again, if we needed to animate a skeleton, I don't know what I'm doing here, we would need to have some sort of starting value, and we would move to the next value. My glass is falling down over my face. As opposed to just jumping from one value to the next value, right? So often you're trying to crank that setting slowly, smoothly from 0 to 1. If you turn that value at a constant speed, so t smoothly moves between 0 and 1, that's linear interpolation. Right. Did I go backwards? Well, here we're. All right. So if we think of these two, whoa. Oh. All right. Remember our math for a moment here. We had our start with A, end up at B. Two main ways to think of interpolation. That blending over the course of several frames. Now, we may refer to parametric evaluation, or blend one step forward from wherever I am now to wherever I'm going, a numerical integration version. So this is a little bit hard to explain in this one particular slide. So let's kind of break it down a bit. I think I've lost my in-between slides. All right. The idea behind this is basically imagine that you said, okay, here I'm at 0, and here I am at 0.5, so I calculate at 0.5, and then here I am at 1, I calculate at 1. And it doesn't matter where you have an equation, it doesn't matter where you were, because now you know you have an equation. I started here, my starting value, my ending value, and I'm calculating where I'm going to be at 0.5. You don't really care, were you just at 0.4? Or you were at 0.3, or did you start at 0? You don't really care about those because you're saying, okay, now I'm at 0.5. I know I'm halfway between, right? So if we can evaluate it parametrically, we can do that. Or if we have this case of incrementally moving and say, okay, I'm moving by an increment, then we may need to numerically integrate. So I think hopefully I have a slide. Generally, games need to use each both parametric and parametric evaluation and numeric integration. Physics tends to use method 2, the numerical integration piece of things, because it moves you along a path, right? You're typically starting at a location, moving there, you're adding to it, you're adding acceleration, right? Each step you are gaining momentum. Many other systems, however, can just use the simpler parametric version. We refer to lerping by all kinds of different names. For example, an audio crossfade, or this simple fade-in effect, is interpolating opacity. We might crossfade between two audio samples, so crossfading. Right. Here's the bottom line. We have the ability to interpolate a scalar. We can interpolate vector 2s. We can interpolate vector 3s. We don't have a special color lerp. We have to worry about that. Write your own. Now, what do we use for t? Seems like the obvious answer is we use time for that, right? So we want to increase with time. Do we use time delta time? We could. We could keep accumulating delta time, or you could save the starting time and use the difference between a start time and time dot time, like we did in that example. Here's the spot the error for those of you who don't want to do the, we'll relive this, I guess, right? The problem here is similar. You know, we get stuck in this dead loop. One thing we might do instead is we could say, well, let's get rid of the while and use the increment of time and fall through. But then we're still stuck in this kind of messy, well, okay, we've got to call that next time in addition to everything and do it in an update loop. So this is kind of the non-coroutine version. You could also compare yet another way. I'm going to say use coroutines. I want to lead with coroutines to make sure we have that covered before we got to this. But it's all that notion of somehow we have to execute in steps, execute at intervals in order to get that smooth, somehow semi-smooth, or get a continuum of changes. Now, did we ever talk about Zeno's paradox? I don't know why we said, we assumed going into here that everyone's heard of Zeno's dichotomy paradox. Has everyone heard of Zeno? No? Yes? Some have? Right, the notion of if you are moving, that which is in locomotion must arrive at least halfway before it arrives at the goal. Right? And the paradox being that if I'm always getting halfway, then I'm spending all my time getting halfway there and I never actually get there. But the cool thing about it that we'll exploit potentially if we're, you know, you want to do a quick and dirty lerp, is you can use something like this, say, well, okay, I always want to be moving towards something, some amount of that distance, right? So what happens if we think about the starting point? Well, we don't think about the starting point at all. We only think about the point that we're currently at. Now, when you start, you're at that point. So in Zeno's case, if I said, okay, starting at this point, move halfway there. So I take half the distance and I move there. Then I'm at a new point. I say, okay, move half the way there. And then so on and so on and so on. So I never care about my original value. I don't care how far I've moved. I just care about not moving all the way to my target, but only moving halfway there. So it's sort of a convenient way, sometimes a dumb way, to lerp. Right? We set the position to 10% of the way between where we are and where we want to go. You'd be surprised how effective that can be. Whenever you want to throw a simple sort of pseudo lerp somewhere in, a little dumb lerp, it fits on a line of code. It unfortunately results in a very non-linear interpolation because you move fast and then you kind of slow down as you get there. Right? So ideally, this is our linear interpolation. Time changes linearly, smoothly as we go from 0 to 1. But the world often doesn't work in a linear fashion, especially when we look at objects and we look at natural motions. And without getting into all the physics of it, is there a way that we can go nonlinear? Because this notion of easing in and easing out is one of the pillars of animation, right? When you're animating something, it starts off slow, it has to build up speed, and then as it hits a target, it slows down again, right? Especially if it's not hitting a target. If I'm just walking along and I'm swinging my arm like in a pendulum, the rate of change, things are slowing down, speeding up over the course of time. So it's easing in and easing out. And with interpolation, there's some easy techniques, some math shortcuts that just turn our simple linear interpolation into something that can do our ease in and ease out by just adding exponents. So instead of using t, we might say, well, use t squared, right? So we'll start slow and work our way up, hit our target fast. So we ease into the motion, and eventually we get fast. We could say 2t minus t squared, and flip the whole thing upside down, backwards. Start fast, end slow. Like slow down as we hit the target. Or, all with just using that same value of t and clever use of exponents, we can both ease in and ease out. Right? So we start slow, reach our kind of maximum rate of change in the middle, and then slow down when we get to the top again. Right? So we can ease in and out by modifying t in place. Right? Normal interpolation, we just use t. When to ease in, we use t squared. When to ease out, we just say 2t minus t squared. Ease in and ease out, t squared times 3 minus 2t cubed. Yeah. So that is interpolation. I'm ahead of time. So let me pull up where's our schedule here? All right. So we talked a little bit earlier, we basically moved our whole talk about some animating, easing, interpolating, and enemy intelligence, kind of pushed that up quite a bit. Because I think I mentioned last lecture, as you're thinking about things in your game, one of the most fun things about the next projects is about, okay, how do the enemies become interesting? How does the environment become interesting? How does it become more a simulation in some ways than just a mechanical, it moves, it does this thing all the time. So we talked a little bit, we already showed a little bit about basic animation. Some of you did take advantage of that, using just, kind of flipbook style animation, drag a bunch of sprites into your game and it'll create an animation for you. So the other things in here, we're going to do a crash course. We're probably going to finish up early today, but I'm going to use the fact that we're ahead of time to fill in one blank, and we'll be able to hit the ground running when we get back, for sure. Very nicely then. Let's see. There we go. So this is the sort of behind the scenes thing there's nothing really, this goes well with the coroutines and why coroutines are the way they are, and kind of good background knowledge of what's going on in the game engine. And all game engines have, some stuff going on like this. And we've hinted at, some of the game physics and why it's important to have, numerical integrations and so on. So let's power through this one, or a bunch of it, say, okay, what's really going on behind the covers? We mentioned those events, we have on collisions, we had on update, we had our own custom things, we had fixed update. How do they all fit together? Why are they the way they are? So running code on time, plus the wheres and hows of game physics and how Unity juggles the execution of everything that's going on. So we'll get some glimpses of the big picture here. Current scene, collection of game objects displayed in a hierarchy. Game objects have a name, a tag, and so on and so on. So we have a hierarchy of objects. Each object has components. Components are provided for you, such as all these wonderful things. How far down the rabbit hole are you ready to go? We'll dive down real quick, but we'll pop our heads back up pretty quick as well. So all the classes that we've written so far inherit from mono behavior, so they can plug themselves in fairly directly into the hierarchy and the execution and so on. And the main thing to take away for now is that we remember that we click on the play button, Unity automatically calls all of the start functions for all of our components on all of our objects. And then every time the frame gets updated, all of the updates happen and so on, right? So you can imagine this sort of big nested loop where I'm saying, okay, for all objects, call all these routines, right? And that happens basically over and over and over again, right? So it iterates over every game object, every component on that game object, calling the update function over and over and over again. We told you about start. Turns out there's a thing you do before you actually start, and that's called awake. And the existence of start and awake, you might say, well, why do you need two things that kind of initialize? Awake is called when an object is initialized even before start. Useful for initializing objects that other object start functions need to know about. You can get crazy. This one can really drive you nuts. You said, well, okay, start needs to have everything in a certain, even start needs to have everything kind of initialized to some reasonable extent before it runs. And sometimes you might say to yourself, well, all right, if all enemies in their start routine, they all need to know where the player is at startup, you may need to make sure to generate a position for the player before all that happens. And you'd put that sort of thing in the awake routine of the player. So you can guarantee that some things happen before other things. Right? We haven't had to worry about that too much. But Unity actually has some means in there. Specifically, this awake, if you know something has to happen before everybody else has their start. You could get carried away. And if you're designing your own game engine, do something that was much more elaborate even than this. But Unity said, okay, there's awake and there's start, so we can set up things that other things to know about, other things need to know about in awake. Interesting thing about it, it runs even if components are disabled, because who knows, you may wind up activating them later on. If you actually want to keep the component from, you need to deactivate the entire game object that it's on, not just deactivating the component, which is kind of interesting, right? So, another one, late update. Kept these secret up until now. Another update function that runs in the main loop, where update lives, but it runs after all of the update functions have run for this frame, and after all the animations have been run and computed. Useful if you want something to happen in the same frame, but guaranteeing that it happens after all the other updates, right? Again, the problem is, just like with start, the order that things are started in is arbitrary, right? It may seem like it's according to the hierarchy, maybe, kind of is, but not guaranteed. So that's why we have awake before start, and we have update and then late update, so we can do things potentially knowing that things have run. So it kind of looks like this, right? Objects awaken or components awaken, then they start, then update gets called, and later on late update gets called. Right? These are pretty familiar. They're part of the mono behaviors. Now, we had on mouse down or on collision, those other things. When do they get called? Right? So user interaction tends to, or gets called at the beginning of the loop, sort of becomes kind of arbitrary. It is a loop after all, so you can kind of think that, on mouse happens after late update in certain ways, because it does, because it's a loop. But it is the first thing gets checked as the loop starts up. So before anything is updated, it does check input at least once. So how does this fit with reality? Now, what I mean by reality is the game engine running physics. So the game engine needs to say things aren't just happening at certain times, they're happening also at certain increments, intervals, and so on. Physics step is calculated in its own loop independent from the master loop, which is why physics can kind of run steadily without physics going totally blowing up, depending on the frame rate of your computer, right? So you can kind of think of Unity really as having two loops being executed simultaneously, or two threads, one for physics and one for the interface, because of this, what's going on in physics, right? So think of physics. Speed or velocity is the distance over time in miles per hour. So how much distance changes over a given amount of time. We often think of speed, though, as the speed we are at that instant, right? This term to talk about the change in immediate sense, where 65 miles per hour, when you're in your car, you look down. You don't look down and think like, okay, I can check my speedometer once every hour. That's, you don't really, you didn't just like look down and say, oh my God, I just traveled 65 miles. You said 65 miles per hour, but I didn't go in a whole hour. I just, so what we're looking at is really kind of a mapping of what we're really doing at the time, right? It's just averaging it over an hour, because that's a useful term. If we gave it our miles per second, you could have a speedometer that told you miles per second, but we're not used to that. Now, distance, on the other hand, how far we've traveled is ultimately the accumulation of speed over time, right? If we travel 65 miles per hour, 1 hour we have traveled 65 miles, meaning we've accumulated that much motion, that distance, right? The sum of speed values scaled by the corresponding time slice adds up to the total change in distance. So if I did 8 hours at 65 miles per hour, you could tell me how far I would be at the end of 8 hours, right? That's what it adds up to. Now, when we think of physics fundamentals, we think, of course, of force equals mass times acceleration. We don't think of miles per hour, but ultimately we can get there from here. And that's sort of how the engine works, right? We have all this wonderful stuff. And often we think all about acceleration, right? Physics is often, one of the main things is about this acceleration. And it kind of is what's going on, right? We have acceleration, which is the change in velocity over time. We have speed, which is the change of position over time. And then position was the accumulation of velocity over time, right? So if we have constant acceleration, that all works. But if we assume that all the rest of them weren't constant, well, why should we assume acceleration is constant? In the real world, it isn't. So we have other things. We have snap, crackle, and pop, which are further derivatives of, they're real things, further derivatives of position over time. Now, depending on your game engine, you may very well take into account all these things, because what's happening is some time interval has passed, and you need to kind of figure out, okay, I'm moving there, or moving, and so on. Right? So under the covers, this is what we're kind of talking about. So it'd be great if it just worked like that, wouldn't it? Right? Nice, smooth function. And every interval we changed by a fixed amount, we would eventually get there. Maybe, well, if we average those, we actually wouldn't get that, would we? Right? We'd have some value below that, for starters. So this is also, of course, assuming that velocity is constant over time, which chances are it's not. So it's changing. So, just like I said before, if we took sort of the average, or you tried to figure out the average of these numbers wouldn't be this number, it would be something underneath it, it would get even worse as we start to take our discrete time slices and try to figure out, well, where we are given where our current velocity is, and so on and so on. So we'd start to get little errors on every time step, and that would accumulate. So you could run through some examples here of saying, well, all right, a car at rest accelerates at 10 meters per second. Where will it be after 10 seconds? Let's just use our traditional acceleration time squared, velocity time. We wind up saying, oh yeah, we're going to wind up at 500. If we did our numerical version and we incrementally went through, we would find that at the end we would actually be at a position of 450, because we can't smoothly, we're in a discrete system, right? So we can't exactly smoothly do that. So it gets even worse if we can't reliably predict the time slices. So if we're taking more time, less time to actually calculate our physics, it gets worse, which is why we have fixed updates. So don't worry, I went through those awful fast. The long-winded way of saying it's important to have something running at a rate that you can generally count on in order to do your physics. All right. That's why we have the physics loop. All right. Runs in the physics loop. Run as regularly as possible. You set that rate in Unity. Set it so it's, I think, defaulted 50 times per second. I don't want to say 50 frames per second. 50 hertz. So it's called at nice, tries to be called at nice even intervals. And this is kind of what it looks like now. We'll revisit our little diagram. And you'll see our physics-related things like collisions and triggers are over there on the physics loop. Right? So we've got interface and animation, drawing, and the real world divided up that way. So here we are. If you want to go to project settings, you actually get the project settings window now. You don't go through this anymore. Wow, you change that. And the fixed time step you can set yourself if you want. So that's why we have a separate fixed update. And one of the reasons we want to put things like anything that manipulates a rigid body in the fixed update is because if you're not careful and the update routine, for example, is running at 300 times a second. Someone had a real crazy monitor, real great graphics card, 300 times per second, and your physics ran only at 50 hertz, theoretically you'd get 6 updates for every 1 physics update. And if you did something as simple as saying, well, okay, let me move based on the first button press, and the first button press is only registered on an update, and you let go of it again, and it gets registered inside another update, it could actually happen before the physics loop even has a chance to run, because theoretically your normal loop, your update loop, could be running even faster, which is why we do things like set flags in one loop and wait for the other loop to react. Right? So here's our good friend again. Love to keep visiting him. And this is the coroutines part. So I wanted to front load the coroutines because I wasn't sure we were going to get to all that. And I guess I can still talk fast enough to get through that. So, that note, have a great break. Think about the way that, you know, your top-down shooter or your asteroids game or your Enter the Gungeon clone or your Toho or your whatever you want to do, RPG, certainly, you want to rewrite Pokemon, all those fit within there, right? Think simple physics, really just using physics probably for your bullets, projectiles, one good use of them. If you want to have, you know, things that skate or fly, you can certainly use physics to simulate those as well. Have fun with it. Have a great break. Any questions, I guess? I should have said that first. All right. Have a good one. And for those, the last few of you, I'll make sure. Dylan. Wait, Dylan's not here again. Okay. Dylan, are you online? For some reason, I'm having the same problem with his submission on Unity again, even though I was able to get at it. We'll find it. We'll work it out. Have a good break.